A climate trend is not just a line drawn through noisy data. It is a claim that something persistent is changing over time, and that this change is unlikely to be random variability, measurement error, or an artifact of how the data were handled. Good climate trend analysis answers four questions. What exactly is changing? How uncertain is that estimate? Can it be distinguished from natural variability? And does it survive reasonable analysis choices? Everything starts with the data. Your conclusions can never be stronger than the data you chose. Temperature is usually easier than precipitation because the signal is larger relative to noise. Extremes are harder still and need different tools. Time resolution matters. Daily data are dominated by weather noise. Annual data suppress that noise but hide structure. You choose resolution based on scientific question, not convenience. Most climate trend analysis uses anomalies. Instead of raw values, you subtract a baseline average for the same month or season. A temperature anomaly is today's temperature minus the long-term average for that month. This removes seasonality, reduces location biases, and makes statistical assumptions more reasonable. Without anomalies, you often end up modeling the calendar instead of the climate. Before fitting any model, you plot. Plotting is not proof, but it is how you avoid obvious mistakes. You look at the raw series and the anomalies. You check the seasonal cycle to justify anomaly use. You may add a smooth curve, but only to help your eyes, never as evidence. You look at histograms for outliers. You look at autocorrelation to see whether today depends on yesterday. And you look at missing data, because gaps and step changes often explain apparent trends. The simplest formal model is a linear trend. You write the anomaly as a constant plus a slope times time plus an error term. The slope gives you a trend in physical units, like degrees Celsius per decade. The slope itself is usually fine. The problem is uncertainty. Climate time series are almost never independent. Warm years tend to follow warm years. Cold years tend to follow cold years. This autocorrelation breaks the assumptions of ordinary least squares. If you ignore autocorrelation, your confidence intervals are too narrow and your p-values are too optimistic. You sound more certain than you should be. There are standard fixes. You can explicitly model correlated errors, for example with an AR-1 structure using generalized least squares. You can use Newey-West standard errors that are robust to autocorrelation, or you can use a block bootstrap that resamples chunks of time instead of individual points. Different tools, same goal. Honest uncertainty. With monthly data, you also need to deal with seasonality. The cleanest option is to compute monthly anomalies first. An alternative is to include seasonal indicator terms directly in the regression. Either way, you must not pretend the seasons are independent noise. Linear regression is not the only option. Climate scientists often use non-parametric methods as a robustness check. The Mann-Kendall test asks a simpler question: is there a consistent upward or downward tendency over time? It does this by comparing pairs of observations rather than fitting a line. Sen's slope then estimates the trend magnitude as the median of all pairwise slopes. These methods are resistant to outliers and distributional assumptions, but they still need corrections for autocorrelation, and they only detect monotonic change. They confirm trends, they do not replace uncertainty modeling. A common mistake is to say a trend is just natural variability, like El Niño. Statistically, you can address this by including known modes of variability as covariates in a regression. You regress temperature on time and on an ENSO index, volcanic aerosols, or other relevant factors. The time coefficient then represents the underlying trend after accounting for those influences. This is not full attribution, but it sharpens trend estimates and avoids misleading claims. Not all trends are straight lines. Climate change can accelerate, slow, or shift. Piecewise linear models allow different slopes before and after a breakpoint. Smooth models, like generalized additive models, let the data estimate a curve rather than a single slope. These tools are powerful, but they trade simplicity for flexibility, and flexibility increases the risk of overfitting. Interpretation must stay front and center. Sometimes what looks like a trend is actually a jump. Abrupt shifts often come from station moves, instrument changes, or observing practice changes. Change point tests help diagnose these shifts, but statistics alone cannot tell you whether a jump is physical or artificial. That requires metadata and comparison with nearby stations. Spatial data introduce another trap. If you test thousands of grid cells independently, many will appear significant by chance. You must account for multiple testing, or better yet, estimate trends on spatially aggregated series or with hierarchical models that share information across space. Extremes require a different mindset. Trends and averages are not trends and extremes. Annual maximum temperatures or rainfall totals are modeled with extreme value distributions. To study climate change, those distributions must be non-stationary, with parameters that evolve over time or with a climate covariate. This is how you make statements about changing probabilities, not just changing means. Finally, be clear about what trend analysis can and cannot do. Detection asks whether change is real. Attribution asks why it's happening. Attribution requires comparing observations to physical climate model simulations. Trend analysis is a necessary first step, not the final word. A practical workflow is simple but strict. Define the question, choose appropriate data, compute anomalies, plot everything, estimate trends with methods that respect autocorrelation, check robustness to reasonable choices, report slopes with uncertainty, and document every assumption. A climate trend is not convincing because it looks obvious. It's convincing because it survives careful statistical scrutiny.